but I'm very happy to be here and to present something. And I hope, yeah, everybody gets something out of it. I'll start with.
Can you just press that OK there? Sorry.
Okay.
Yes.
Yes. No. Why doesn't this work? Okay. I'll do it. Okay. So when you talk about climate, or when we talk about climate, very often, of course, we are interested. How warm will it get, right? And there are CO2 emissions, there's CO2 changing in the atmosphere, and we want to know how warm will it get in a specific year, in 2100, but maybe also later or earlier. And when you go to observations, this is a time series from 1850. And the black line is what we have observed, more or less, in global mean temperature. There are a number of simulations, so it's also in the brownish shaded area, and you see, well, the temperature are rising. But one question you might ask is this continuing like this? Is this going to steadily rise, or will there be any jumps, maybe also forth and back? And of course, I mean, the goal is very often named 2100, but we might be interested also in what happens thereafter, right? I mean, is it going to go back or even more warming and these kind of things? Now, if we think about on a long time scale of Earth's history, then I'll zoom in a second here. Then you see that this time series from 1850 to present, more or less, is a very short time series. And what you see here on the right are some projections for the coming centuries, up to 2300 from climate models, of course. Depending on which scenario you use, you get to very warm temperatures, right? But even the lower ones very easily get out of the, okay, this is maybe better to see, get out of the regime that we have observed in the black line, right? But there is actually much more in Earth's history. So if you expand this information to the paleoclimate record, then, and I'll explain what that actually is. So this is 65 million years ago, starts on the left and goes up to here. But the time scale the time axis is not continuous, right? So it starts with steps of 5 million years, but then here is 1 million year time step. So it zooms in when you go to the right. And this is on the y-axis is an estimate of global temperature or deep ocean temperature, something like that. At least temperature on Earth, you could say it, and it comes from a collection of different proxy records. So it comes mostly from sediment cores in the ocean and different parts in the world, and it measures oxygen isotope ratios and different kind of things that give you an idea or give you the way to reconstruct what the temperature has been on that time. So, and if you put that together, you get to this estimate of temperature. I mean, the absolute values are have quite some uncertainty on there. But what you see is that in the early part of this Earth's history, you see very warm periods. You see here in the later part, you see these large swings that we know as the ice age cycles. But in between, you also see a gradual cooling, but you see some very rapid steps in between. So a lot of things have happened. What is shown here in the lower part of the graph is a reconstruction of the CO2 concentration in the atmosphere. That is typically thought of as having an even larger uncertainty. But also there you have higher CO2 ranges, you have lower CO2 ranges. And if you compare these scenarios, then particularly the higher ones, you need to go very far back in time before you meet a similar part there. Now, so we know quite a bit on what has happened, but of course we have not observed this directly, right? These are all indirect measurements, so it makes that complicates things a bit more. Now, if we, as a physicist, if we would would have such a very long time series at very high temporal resolution, we could make a spectrum of this, right, to see what is the variability. Now, of course, we cannot do that, but we can draw it. We can at least make a sort of an artist's view of the variability that we know. And this is here. So this is a spectrum. So it has periodicities on the x-axis, and you start out with very short periods and go up to very, very long periods. But each of the parts of the climate system, of course, have their individual internal timescales. Now, one very obvious one is the daily, that comes from the external rotation of the Earth, and the yearly cycle from the seasonal cycle, right? So these are sort of externally imposed frequencies that appear as very sharp peaks. But then for the atmosphere, we have, well, days to decades maybe as variability. For the ocean, it's a bit longer. These are the typical timescales. And when you look at these more broader peaks, there are a lot of acronyms. I'm not going to explain them all, but these are more internal modes of variability, right? Like the ENSO is the El Nino phenomenon that has a periodicity of 3 to 7 years. These are all processes within the atmosphere and the ocean that generate that without any external forcing. And there are more of these in all kinds of other systems. So one thing that you wouldn't see, even if you have a very long time series, you make a spectrum out of it, is if there is one or a few very abrupt transitions in there, right? That you wouldn't see that in a spectrum. But we know, of course, there are a number of so-called tipping elements in the climate system. These are different subsystems that could potentially generate abrupt transitions somewhere. Now, you might have seen this. There has been 2 global tipping point reports now in 2023 and 2025, where you might have seen this picture before. There are a number of parts of the climate system identified as potential tipping elements. Many are located in the biosphere, in ecosystems, actually, in different regions of the world. But a lot are also related more to the ocean and atmosphere, to the ice. So one very prominent one is this pink stripe here that represents the Atlantic meridional overturning circulation. The ice sheet on Greenland and on Antarctica, the big ice sheets, right? They are also considered to be tipping elements, but there are many more. And I'll touch upon a bit on these ones here later in the talk. Now, of this tipping point report, one of the latest one of the main messages basically was it looks a bit like the first tipping point has already been reached. These are the coral reefs, and I'm not going into a lot of detail in there. But if you look further in this list, when the warming increases, it turns out that ice sheets and ocean circulation are very close, actually. And that is something new, because previously it was considered that this is still very far away. Of course, there is quite some uncertainty in there, but in particular, the ocean and the interaction with the ice sheets becomes interesting here. Just to introduce you very briefly what the Atlantic meridional overturning circulation is and what does it mean as being a tipping element or a collapsed state. So currently, on the left, we have the situation that there is the Gulf Stream, of course. We have it in the North Atlantic. It brings a lot of warm water to the Northern Hemisphere, particularly into the Arctic or towards the Arctic towards Europe. And that makes the climate in Europe quite a bit milder than on the same latitude on the North American continent, for example. Now, it brings a lot of heat there. while it goes there, the water, it cools, of course, because it gives its heat to the atmosphere. And then it is also relatively salty, so it can sink down to deep, to the deep ocean, basically. And there it returns in the blue line. So that is the Atlantic meridional overturning circulation. And it is possible, at least that's the idea, that when there is more fresh water coming into the North Atlantic, for example, from a melting ice sheet or from melting sea ice, or also simply from more precipitation, the water becomes less salty. So it is less easy to sink it down, and that's why it could weaken this overturning circulation. It does not mean that the Gulf Stream is going to stop, but the Gulf Stream will be maybe a bit weaker, and in particular, it will not have this strong extension towards the north, right? That's what we mean with the collapsed Atlantic meridional overturning circulation. Now, I'll go through a number of concepts here in the beginning, because this is going to come back. When we talk about, yes?
So if you mentioned that it won't suddenly stop the Gulf Stream, it will just get a bit weaker. How do you identify a difference between that being sort of a tipping point, which has sort of discreteness, versus just a gradual change?
Well, no, yeah. Okay, that's a good question. I mean, it doesn't mean that this can be still an abrupt change. And what is abrupt there is that the deep convection, so the deep water formation, stops. So while the Gulf Stream itself is sort of a horizontal wind-driven current, the wind is going to blow still, so this will going to continue. But what will stop is the deep water formation, and so the heat transport towards the north can relatively abruptly stop. So that's the more discrete one. And then I think another thing for being a tipping point needs also to be that if you go back with your forcing, you cannot return easily, right? The history is
a lot of salt in the north.
Yes, that's difficult. But you could build up the ice sheet, of course. That would mean that, but that you need to go back quite further than for the initial point. So there is a hysteresis in there as well. Yeah. Okay. So when we think about the global temperature, then one of these metrics is climate sensitivity, in particular equilibrium climate sensitivity, where all of the IPCC reports and people talk about this. And this is a relatively, it sounds simple, the measure. It is a linear measure. So we talk about doubling CO2 concentration that induces a radiative perturbation. If there were no feedbacks within the climate system, that would directly translate into a temperature increase because of the increased blackbody radiation, right? So that's what we would call the Planck response. Now, of course, within the climate system, there are a lot of feedbacks. So that alter the initial perturbation. So the actual temperature response can be quite a bit larger. Could also be smaller, but it is a bit larger than the Planck response, because there are also processes and feedbacks within the climate system. But that is how the equilibrium is defined. So you take the eventual equilibrium change in temperature after a doubling of CO2 and divide it by the forcing, the initial perturbation. Now, how do we determine that? It has a lot to do with the radiative imbalance that you introduce at the top of the atmosphere by the forcing, but then you have a radiative response, a very quick response within the atmosphere also, and you might also have some variability in there. This is this V. And then typically what you do is you do an expansion up to first order. So you say the initial Planck response, that's the direct radiative response plus a linear term on these alphas that depends on different processes within the climate feedbacks, well, climate feedbacks you would call them. Now the variability, you can say, okay, we talk about equilibrium, so over very long time scales, this would average out. So we can consider that to 0. And then the equilibrium sensitivity is simply given by this first linear term that determines how strong are the feedbacks within the climate system, right? Now, in practice, what is very often done is that we impose a big CO2 perturbation, so abrupt 4 times CO2, for example, in a climate model. And then you get quite a strong radiative imbalance in the beginning, and you can extrapolate down to where this radiative imbalance goes to zero linearly, and you find, well, this feedback factor or the equilibrium climate sensitivity. That is what is being done in practice. And also in practice, typically you use 150-year simulations with all kinds of different climate models. Now you can already anticipate that there might be a problem here, because what is equilibrium, right? When you think about this enormous amount of timescales within the climate system, these 150 years might not be enough to get everything in equilibrium, right? But only a part of the climate system. You can try to determine that also from observations, but there are not that many. But it uses similar concepts, actually, that you extrapolate to to the zero radiative imbalance. You can also use paleoclimate reconstructions, but then the equilibrium concept needs to be reconsidered a bit, because you act on very long timescales, so you can think about what do I actually compare with each other. Yeah.
Does this also mean that if we would stop all CO2 emissions today, that only in 150 years the climate would kind of settle?
Well, no. Yeah.
Okay.
You mean when you would assume that in equilibrium?
Yes, but supposedly this 150 years is chosen as sort of a reasonable settling time.
Yeah, I think, well, yeah, I'll come back to that also. It is chosen as a settling time for some processes. And I mean, if you think of atmospheric and surface processes, that is reasonable, actually. Yeah, so in that sense, it is okay in many ways. But if you look at paleoclimate timescales, you have changes in large ice sheets, right, over thousands of years. Then it becomes a bit troublesome. But yeah. Okay, so this is just an overview about what all these feedbacks are. I mean, the black body radiation, the Planck feedback, that's actually a negative feedback, and it is very strong. So in total, the total feedback estimate is always negative because of the Planck feedback. And it is also good that it is like this, because otherwise you would end up in a runaway climate, right? But the other processes, some of them at least, add up or have positive feedback processes that add up to this negative Planck one. So that's why the temperature response is just larger than the original one. So a strong one, positive one, is water vapor and lapse rate feedbacks in the atmosphere. Clouds are a very uncertain feedback, actually. They can be either positive or negative depending on where they are on Earth and whether they're high or low. In total, they are estimated to be a positive feedback on there. And the surface albedo is also a relatively strong feedback that has to do with the fact that when you have a relatively white surface of sea ice cover or ice cover, for example, that reflects a lot of radiation. But when you melt that and it gets warmer, then this reflection is no longer happening, so you get it even warmer, right? So that's why this is a positive feedback. So with all kinds of information from climate models, from theory, from observations, these different feedbacks have been estimated to get a typical value of this equilibrium climate sensitivity ranging between 2.3 and 4.5 degree warming per doubling of CO2, I should say to that. Now, what I will go through here in this talk is
these feedbacks are we still talking about the ammo, or
well, they
or is it like more
these are in general, these are feedbacks anywhere within the climate system that affect the global temperature, and the AMOC could be part of that, but I mean, it is a more regional one, as many of the tipping. I'll come to that as well. Yeah. So in principle, yes, that could be in there. I think I will briefly show we need to talk about timescales and what actually equilibrium is. I mentioned that already. And then in particular, when we go to paleoclimate for determining the global mean temperature response, it is not necessarily the case that these feedback processes are actually constant over time, right? They can they can change over time. Then if there are tipping elements, tipping points within this time series that cause abrupt transitions, then we get into trouble with our regional or, well, short time scale equilibrium. So I'll get a bit more details into that. And in particular, when we have these short simulations like 150 years, and we know there are actually tipping points, then the nonlinear processes can complicate this estimation, although this extrapolation actually a lot. I'll show you in the end an example where it looks like you estimate the right value, but then after 1,000 years, something big happens, actually. Okay, so here is again an overview of the different processes and the different timescales within the climate system. These blue arrows are relatively long because there's never just one timescale for each system, but it has a whole range timescales. Now, what we do for estimation of climate sensitivity simply on practical senses, we make a cut at about 100 years, say everything that is slower than 100 year, or slower than on 100-year timescales. These are the slow processes, like ice sheets, part of the oceans, and so on. And the fast feedbacks are the faster processes that are included in many of the IPCC climate models, actually, and that settle within decades to up to 100 years, right? And then the evolution of the temperature in the global mean would simply be given by, you have some forcing, could be CO2. You have an evolution of the slow processes. You have an evolution of the fast processes, radiative forcing, and you have the outgoing long wave radiation in there, in balance. Now, if you then estimate climate sensitivity, also from paleoclimate, one relatively simple thing you can do, you take two states in time, you compare the temperature with each other, that gives you the delta T, and you divide it by the change in CO2 concentration over that time, right? That gives you the Earth system sensitivity. It doesn't say anything about feedback slow or fast. It is simply everything included in there. And it gives you a number of values. So on the left graph, you have on the horizontal axis, you have atmospheric CO2 concentration. The vertical line is the present day state. And on the vertical axis, you have global mean surface temperature. You see these red bullets, they come from different periods in the past. You see one that is colder than present, that's the last glacial maximum. But you see a number of them with very warm climates. These were from the, say, before 30 million years ago, from the very warm periods in the past. And you can make estimates of what the equilibrium temperature where they are depending on the atmospheric CO2. Now, if we want to have what we call the equilibrium climate sensitivity with this 100-year timescale in mind, we need to correct for the fact that maybe over these long timescales, the ice sheets have changed or the vegetation cover has changed, right? And so that needs us to know what ice sheets were there in these different times and translate it into a radiative perturbation that accounts for the change in ice cover. This is in ice cover, it's mostly the albedo, but for other things, it could be other processes. So if you do that for all the known slow processes, then you would end up to an approximation, at least, of what we call the equilibrium climate sensitivity. Now here, this is this has been done here on the right graph. It takes the same periods in the past in these the red points, but it has been corrected for what is known about ice sheets, about vegetation cover, and some other processes in there. And then you see that these numbers for the warm periods also, they sort of fall into this blue area, which is the IPCC climate model range of equilibrium climate sensitivity. But some, I mean, they have a huge uncertainty, of course, but some seem to lie a bit above that. Some also lie on the lower end, but at least they go within that same range. So that at least tells us they come into the a similar range, and that also is sort of reassuring that we estimate the right thing here. Now, from a dynamical systems perspective, it's interesting, I think, to look at how this temperature evolution looks like. And now this picture now has say, the glacial, interglacial cycles more or less in mind, right? Where you have a region, if you plot temperature versus radiative forcing or CO2 or something like that, you have a region where it is relatively warm. So these black lines denote trajectories of the climate system. You might have a transition to a cold glacial state somewhere, and then it stays a while there. It might get back relatively quickly to the warm state and so on. So that is the idea of having a region in the phase space where typically the climate evolves on, right? Now, if we ask now, how could we estimate from such a maybe a time series where you know that it evolves on this attractor, how could you estimate climate sensitivity? You would take 2 points in time, right? Compare temperature and CO2, maybe ice sheets to each other. So the climate sensitivity is given by the slope of the line between the 2 points that you take in your timescale. Now, if you happen to do this here, in that region of the attractor, you will find a different slope. So that represents actually the background state dependence of the climate sensitivity if you estimate it in this way, because in a cold climate, there may be very different feedbacks active that determine the response to CO2. And indeed, if you collect a lot of paleoclimate information from warmer and colder climates, and warmer is relatively loosely defined here, many of the warmer climates come actually from not so far back, so from the previous interglacials that are a bit warmer than today, or some come from these very distant times in the past, but not that many. But at least what you see is that, so the blue distribution and the red distribution, these are from cold or warm climates, the estimates of climate sensitivity. You see that here it looks like the maximum for the cold climates is a bit lower than the maximum for the warm climates. Now, of course, there is an enormous uncertainty on the observations themselves, right? And that might explain part of this distribution width. But one thing that could also be, and what I'm trying to go a bit deeper into, is that because we have such background state dependence, you will always get the distribution, even if you had exact measurements in there, because the feedbacks are varying over time or with the background state. So you will not, I mean, this equilibrium climate sensitivity cannot be just a single number. Now let's go back to this idea of the climate attractor. The say mathematically the best way to estimate the local slope on this attractor would be simply the derivative of this function radiative forcing versus temperature, right? But that requires to so then you would. From your time series, you would go to the closest point on the attractor and you would determine the local slope. These are these blue lines given there. But that requires that we know the attractor, and typically we don't know the attractor, right? So you can do approximations. So what you also can do, you can choose different points in time maybe with a fixed time delay between the two on a time series. So you start from point A and you wait some time and you end up in point C, for example, and the slope between that gives you at least an idea of the incremental sensitivity. Sometimes when you have a different trajectory, you might end up in point D, right? That will give you a very different value for climate sensitivity. And you can generalize that a bit and take all kinds of time delays you can think of in your time series, and you can put them all together into one distribution of 2-point or incremental sensitivities in there. When you think of this from an energy balance point of view, what that would mean for climate sensitivity, then so I'll take a very simple approach to the climate evolution here, but with sort of specific processes in there. Now you have the Q0, that's the incoming radiation from the sun. The albedo, if that depends on temperature, so when it's warm you don't have ice, and when it's cold you have more ice, then you have to impose a specific temperature functional form on that. You have another part that can be temperature dependent, that is the emissivity, that represents a bit how many clouds are there and where they are. So it's not a pure black body radiation that's outgoing, but a slightly modified one. We have a CO2 forcing, a typical term in there, that how the CO2 concentration translates into radiative forcing, and you can add some noise to that whole evolution of temperature. That gives you this typical bistable structure. So when you plot temperature with a CO2 forcing, you get a warm climate, you get a cold climate, and you have some unstable state in between. Yes?
So I was just wondering, is there not a kind of memory in the system?
Yes.
That you also store all CO2,
yes.
for example, in the water. Where is this memory?
Well, in this case, what you can store is energy or temperature, basically, so heat, and that sits. The memory sits in this constant CT, so the heat capacity actually. And you can vary that depending on whether you also look at the ocean or only the atmosphere, surface, and so on. Yeah. So this is very much simplified, but it sits in that one. Yeah.
So that's it's a good question. So we're only looking at temperature.
Yeah.
But actually, it's not clear that surface temperature comes from distributing heat differently versus storing more energy from the sun. Right? You disentangle these, I guess.
Well, one thing that the amount of energy that comes from the sun, and then a part of this energy will store within the oceans, more or less, or within the system. And the other part, sits at the surface, is also reflected back, so that is a much faster process in there. Now, you cannot exactly disentangle it. That's why the equilibrium is a bit of a problem. But what you typically assume here is that you have a timescale separation, so that very often the deep ocean is not considered because it's too slow. And you focus on, say, the surface layer, more or less, that has a certain heat capacity, so that gives you a typical timescale in there on that evolution. Yeah.
Where's the heat to the powerful coming from?
That's the black body radiation that goes back to space. That what is depending on the temperature of the Earth that is going back in there. That closes the balance actually. Yeah. Okay, so this is of course in a way constructed, but indeed because of this timescale separation, also we are able to prescribe this function of the albedo, right? Because it assumes that there is, on very slow timescales, there is a change of ice sheets, but it's not explicitly resolved here, and it doesn't enter into the heat balance in there. But when we impose it like that, we end up with, well, this typical structure of a warm and a cold climate, with having the two equilibria in there. And if you add noise to that, so you sort of explore this attractor, you never really meet the unstable state in between, but you are, for a while, the time series sits in the warmer one, and then it transitions to the colder one, and then sometimes also back. So that's what you would observe from such a energy balance model.
To go back, you would have to go to the other bending point.
Yeah, exactly. So if you okay, so this is CO2 forcing. If you start out here and you increase CO2, at some point you will jump here, and then you vary CO2 maybe just a little bit. You stay on the warm state, but when you enter here, then you jump back. Something, yes. Yeah.
So this sensitivity, somehow, if you accidentally measure it in these two different,
yeah,
you compare points from these two different regimes, it can diverge.
Yeah, exactly. Well, that's exactly what I'm going to show now. That's the interesting thing. So what you see here is it is a slightly more complicated model than what I just showed. It's not just the energy balance of the atmosphere, but it has well, it has a simple version of the ocean, and it has a very simple version of ice sheets as well that are switched between, well, a lot of ice and little ice in there. But it generates, in terms of this temperature CO2 relation, it generates a very similar climate. It has a warm climate on the top, and it has a cold climate, and it, depending on the forcing, it can vary sort of periodically between that, representing the ice age cycles, right, on 100,000 year timescales. Now, if you take this estimate of the attractor, or a very long time series of that model, and you use the incremental climate sensitivity, right? You pick all kinds of time distances, and if you only do that for the warm climate, so above the red line, more or less, you get a distribution of climate sensitivity. That's shown here. So here is climate sensitivity, so the slope between 2 points, basically. And you see mainly a distribution that comes from, well, this pink part in the warmer climate states. What you also see is you see a little shoulder of not so probable, but sometimes very high values. And that exactly comes from well, I have to go here. It comes from this region, or maybe also from this region, right? When you are just in these transitioning states, these very high values. You can do a similar exercise for the cold climate, so below the red line, and you find then this distribution again, a typical one with some very high values that are not so probable. And now here below the warm state distribution, what is shown is the probability of transitioning from warm to cold. That is very high in this region here. So exactly when these not so probable values of climate sensitivity occur. And a similar thing is true when you look at the cold climate states. So that tells us that, yes?
So these timescales that we're looking at here are about, so yeah, right now 20,000 years.
Yeah.
So to what extent are all these parameters in your model reasonably constant? For example, the influx of solar energy, I mean, you have these Milankovitch cycles. Yeah,
you can add them on top of there. I think, I think in this simulation, it was actually on there. You have the Milankovitch cycles on top of there. They generate, they have also something to do with these ice age cycles in there. But at least in this model, they do not drive them. I mean, that synchronizes to that, but there is in addition an internal one. You get the similar glacial cycle also without this Milankovitch forcing, actually, in this model. I mean, because there need to be some feedbacks that make the amplitude so large. But this can be sort of included in there. Yeah. I think maybe I was wrong in saying that in this simulation we had the Milankovitch cycles in there, because then you would see a bit more spread in the warm and the cold climates. but you can include it in that model. Yeah. Okay, so one thing that it tells us about these abrupt transitions is that if there is in any paleoclimate time series, if there are abrupt transitions, then what we will find if you estimate climate sensitivity, you will find quite large values, quite extreme values. And why is this? Because this is simply, yeah, it is mostly because we have this hysteresis behavior. So we have these two equilibria. So the upper row shows you what the same picture as I just had before. On the left, the temperature versus CO2 state graph, and on the right, the distribution of the climate sensitivity estimated from that climate state, but now not divided into cold and warm, just everything. And so that's why you find these two peaks in the distribution, which is cold and warm mean. So you get this bimodal distribution, and you also get these extreme values here from the transition period. Now you can modify in this model, you can modify your albedo contrast a bit that you don't get glacial cycles actually anymore. So you can you get more gradual changes between cold and warm actually. So then the left graph in the middle looks much more gradual. You don't have this unstable state in between. You don't have very abrupt transitions, but you still get a warmer and a colder climate, right? And the distribution of climate sensitivity is still bimodal because you have different feedbacks in the colder climates than in the warmer climates. But you don't have tipping anymore, so you don't really see these very extreme values that much anymore. If you further modify the model and you completely remove the albedo contrast, you just get a linear relation between temperature and CO2 more or less. And then you get just a unimodal, more or less Gaussian distribution, which is quite boring and quite unlikely to happen. Yes, I think you were first.
So just looking at the bottom graph and working out,
yeah,
it does look like when there's no albedo contrast, both warm and cold collapse into one regime with the same equation, and then slowly becomes bimodal. But is this sort of continuous in the sense that the more you turn up the albedo contrast, the more the two modes of the gradients diverge? Because in the final graph, they still seem quite close together. So what you start from like zero, you start from like one gradient, then the gradients become slightly different.
Yeah, you move it a bit out. Yeah,
but then they don't get extremely different. They just they stay slightly different.
Yeah, get this.
Yeah, but I mean at the very top,
you cannot really pull them apart.
Right. Yeah. Well, I guess I'm something about the.
Well, it depends a bit on the function you impose in it, but what you need is yeah, you do. I think you do pull them apart actually, because what you increase here is the contrast between high and low albedo. And the more you do that, the more you get a separated state of warm and cold climate with abrupt transitions in between. It is not really a smooth transition between the two, I think. Yeah, yes.
It seems like in both the top and the middle scenario, actually the most likely sensitivity to measure is larger than 2.5.
Yeah.
Right? It's hard to see, but this right axis seems completely filled in, which I'm assuming is the aggregate of everything larger than 2.5.
Oh, yeah. You mean this? Yeah.
Yeah. So basically, in either scenario, you're probably going to measure a very high sensitivity.
Yeah, that's true. That's right.
So how? And the problem is that in real life, you can only do one measurement because you're only in one situation, I guess. So
well, if you have a time series, you can at least have a few.
Right. Okay.
Yeah. But it's
20,000 years.
Yeah. Well, one thing that has changed here from here to here is the density axis. So this is much less likely to measure anyway, right? So what you probably
The densities have to sum to 1.
So I guess it's,
Yeah,
yeah.
yeah. So this comes because we cut it off here at 2.5 basically. But
So actually,
maybe also because the time series is not long enough, but you would have to.
so that peak for 2.5 actually extends way up, also in the
Yeah.
middle float. Yeah, yeah.
Yeah, and then you have one here as well. That is.
So yeah, so I would imagine that makes it very hard by just measuring in real life what sensitivity is, determine in which scenario you're in.
Yeah, it makes it hard.
Because
I
you
mean,
tend to be on the extreme.
even to distinguish between these two peaks there, you would need quite a long time series and a lot of measurements in between there.
Yeah.
Yes, that's true. That's right. But I mean, we have a number of ice ages, right? So you could, but yeah, it turns out that in practice, this is very difficult to distinguish between. Yeah.
Well, you show these two different states, and which are based on the albedo, and I think that's because the albedo is one of the factors in your equation which is changing.
Yeah.
But there are much more tipping points.
Yes.
In your system.
Yes.
Yes. I think then it would be much more complicated.
Yes. Well, the real world is more complicated. I agree. Yeah, that's true. I mean, the reason why I talk here mostly about the albedo, or why I take this as the first thing, is that this is one effect that really affects the global temperature. And that's where we look at when we talk about climate sensitivity, right? Well, many of the other tipping points do not directly affect the global mean temperature. I mean, like the AMOC, for example, it warms or it cools in the northern hemisphere, but it warms in the southern hemisphere. So it is not such a direct effect on there. Very often it is regional. But it's true. I mean, if there are more, and I think I'll get to that. Yeah. Okay. I think I'll do this very briefly. So indeed, I mean, when we look at these kind of, say, attractors, what we have in mind is a glacial and an interglacial state, right? And these are on long time scales, quite some changes. And the albedo plays a big role there. The CO2 probably also, but also the Milankovitch forcing and so on. Yeah.
So about the time series, so I was wondering, what I understand is if you go back to the previous glacials and the interglacials, the CO2 is fluctuating a little bit.
Yeah.
But the CO2 concentration as we have currently is without any precedent. So
yes, well, yeah, that's true.
How do you include this?
Well, in this model context, we don't look at the current CO2 concentration. So we really consider, say, glacial, interglacial changes, which are relatively small. If you go back further in time, you get to higher CO2 concentrations. It's not so clear whether this is, well, there is still, I think, a period in the past where it's as high as it is now, and maybe even higher. But yeah, that is quite far back in time, not within the Ice Age cycles, yes. Yeah, well, just after the dinosaur, the Eocene is quite a warm period, yeah. Okay, so we have all these tipping elements, and many of them are quite regional in their impact. Well, now, one way they could impact the global temperature is if they connect to each other, and they are, of course, connected to each other. So this is just a hypothetical idea of such a cascade. If you melt the ice sheet, you affect the AMOC, right? You put fresh water in there, it might collapse. You get shifts in rainfall patterns that could affect the rainforest or other regions that are really important for also the CO2 budget, right? So in that sense, it is possible that you get in such a situation, you can measure your from your time series, but then with a climate model, what we do currently is we put on a big perturbation, so we move away from the attractor, and then we wait until we go to the to a new equilibrium, right? This orange point there. Now, if there are cascades of or carbon cycle feedbacks or something else, you might up in a different equilibrium, right? Or you might even up in a lower equilibrium. We don't know that depending on which way the feedback really goes. So in this way, the cascades or the tipping elements that can affect either the global mean temperature or the CO2 budget, they can have an effect on these kind of things. Now, let's go back to this graph I skipped over here. This is it's a complicated picture, but it's sort of the main idea we have currently about the interactions between different tipping elements. And so one thing you see, for example, in the center of the Atlantic, there is the AMOC. It has a lot of connections to other tipping elements, to ice sheets, north and south, to forests, to monsoon circulations, and so on. The red arrows indicate something that could be destabilizing. The blue arrows indicate connections that could be stabilizing. One example is when you collapse the AMOC, you get it colder in the northern hemisphere. So that might stabilize the Greenland ice sheet, right? Because it actually gets colder there. But there are other, and the other way around, it is more destabilizing because when the ice sheet melts, it would affect, have a negative effect on the AMOC collapse. So this is a complicated picture, but that's why I would like to zoom in a bit and take a little part out of it and get into a bit more detail what these cascades or interactions actually mean. And what I will do is take a brief excursion to a situation where we have a Greenland ice sheet, the AMOC, and the West Antarctic ice sheet. There is more in there, like the Superloggia and sea ice and so, but that I'll leave that out for a while. But let's think about it, what that actually means, this coupled system of interacting tipping elements. So I mentioned already some of these connections. When you melt the Greenland ice sheet fast enough, you would put a lot of fresh water into the North Atlantic that could potentially shut down the AMOC, right? Although these two have very different timescales. The ice sheet acts more on millennia, whereas the AMOC decades to centuries, maybe. And the way back could be potentially stabilizing. You get cooling, but you might also get changes in precipitation. So that's not so clear. Now, when you then also include the Antarctic ice sheet, when that melts, it puts fresh water into the Southern Ocean. So it is interesting to look at what does that do to the AMOC. And the way back, I'm not going to talk too much about that, but there's also, of course, when the AMOC collapses, it cools the northern hemisphere, but it actually warms the Southern Ocean. So that might help to melt the ice shelves of Antarctica. Now, we started out looking at this in a very simple system. So we have a simple land ice sheet on Greenland that has just this height surface mass balance feedback. We have a marine ice sheet on Antarctica, again, in very simple representation, a circular shape and so on. And in between, there is an ocean consisting of 3 boxes where you have temperature and salinity. So when you have an on state of the AMOC, you would have sinking in this box and upwelling in the other box. And when you have the collapse state, you would have the opposite in there. Now, this is forced by fresh water and temperature from the atmosphere, specific fluxes, and these are connected by having, when you raise temperature on Earth, this ice sheet, for example, melts. It puts its fresh water into the northern box. Similarly, the southern ice sheet, when it melts, it puts fresh water into the southern box. There is a coupling back also to the Antarctic ice sheet when this third ocean box, the southern ocean box, gets warm enough, it has more impact on the marine ice sheet, right? So this is just one parameter, but it says, well, when this temperature 3 gets warm enough, you get more melt in there. Now, the interesting result here is that depending on how strongly you connect the southern ocean box with the marine ice sheet on Antarctica, you get cases within this blue region here. So here's the coupling strength between the box and the West Antarctic ice sheet. In this blue region, you get cases where even though the Greenland ice sheet melts and the West Antarctic ice sheet melts, the AMOC does not collapse. Well, in the yellow region, it does. And this also not only depends on the coupling to the ice sheet, but also it depends on whether the southern ice sheet melts before the northern ice sheet or the other way around. And it particularly occurs when the West Antarctic ice sheet melts early enough and also fast enough. You can expand that a bit into a slightly more sophisticated ocean model. So this is, again, it is still an ocean box model, but it is a bit more adapted to the current situation of the Atlantic. That's why you have more different boxes, and you force it again by freshwater and temperature. Now, in this situation, we left out the dynamic ice sheets, but we represented the input from the ice sheet as the northern freshwater input and the southern freshwater input, which you can then vary whatever we like. So, for example, one sort of control case is that you, here this blue line, you let the Greenland ice sheet melt in 1,000 years, right? That gives a certain freshwater input in there. If you do that, then the AMOC, that's the lower line here, that collapses at some point. If in addition you add freshwater to the south, that's now a hypothetical Antarctic ice sheet melting, this yellow line here, then already this example shows you there is a case where they melt more or less at the same time, the Antarctic a bit earlier and a bit faster. The AMOC weakens a little bit, but it doesn't collapse, right? It is stabilized again. And also in this model, you find a region depending on how long it takes to melt the Antarctic ice sheet, what the delay between the two ice sheet freshwater inputs are. In this blob here, you find no AMOC collapse. Now, within such box models, we can sort of understand why that happens, because in the south, in the Southern Ocean, if you affect the density negatively, you actually strengthen the current AMOC situation, while if you put it in the north, you destabilize it. So depending what comes first and what wins, you can actually stabilize it in there. Yeah.
So this is a very naive interpretation, but if I look at this blob in which we're kind of okay, that seems like it would be reasonable to say that we are in fact in there, right? So
well, yeah,
it's going to take 1,000 years for this thing to melt.
That's true. I mean, we have chosen these ice sheet dynamics, of course, on what we think could happen. Mm-hmm. The Antarctic ice sheet could melt quite a bit faster and earlier than the Greenland ice sheet. That's true, but this is still a very simple model.
No, we're talking about the marine ice sheet, not
yes,
the terrestrial ice sheet.
Yes. We talk about mostly the shelves, the West Antarctic ice sheet. Yeah. That's right.
So what is that? What's the difference? Is this like floating ice?
Oh, maybe I get back to this. Where is it? The map. Well, here you maybe you see it. So the Antarctic continent is completely covered with ice, right? But a large part of these ice sheets are actually floating shelves, and on this side here, that's what we call the West Antarctic ice sheet. That has a It has a part of land that's not that big. I mean, this east part is much bigger, but it is sort of supported by the fact that you have these floating ice shelves. So if you remove the ice shelves, then this part will float down into the ocean very quickly as well.
Right.
Yeah.
And they're extra sensitive to water temperature.
Yes, exactly. Melting from below. Yeah.
Right.
Yeah. Yeah. Okay, but to come back to your question, I mean, it might be, but these are still very simple models. And also one thing is, I mean, maybe the AMOC does not collapse, but the two ice sheets still melt, right? So I'm not sure this is good news. Yes,
And
exactly.
the ice sheet connected to other tipping elements apart from AMOC?
Yeah, well, they are probably connected to sea ice and these things, but I think the AMOC connection is one of the strongest ones. Yeah.
By how much do sea levels rise? We've lost Greenland and the West Atlantic ice.
That's quite a bit.
7 meters.
7.
Greenland is 7 meters, and West Antarctica is also quite a bit.
Same way.
Yeah, yeah,
Then
it's quite a lot, but it's on long-time scales, right?
Yeah.
Now we went one step further in this model hierarchy, try to understand why this AMOC stabilization really happens, and also a bit going into direct, is this something that could happen on well, currently or so? And as I said, in this box model, simply the density in the north and the south is affected. But of course, the AMOC is more than that, and it has a wind-driven part and so on. So what we tried here is similar experiments within a so-called intermediate complexity model that has it has a three-dimensional ocean and atmosphere on a relatively low resolution. And that's why you can do a lot of experiments with it. But it is not like the IPCC models, the future ones, right? But at least it is more than a box model. And it also has it can have dynamic ice sheets, but in this case, we imposed a lot of different forms of the freshwater flux in there. So we did similar experiments as before. And here is a melting of Greenland in 3,000 years assumed. That's this blue one, and the freshwater is put around Greenland into the ocean. And then the AMOC is constant first, it collapses relatively quickly, and it stays in an off state for at least 1,000 years. Now, in this model, when the Greenland freshwater input stops, it actually recovers again, but it stays in a low state for a long time. Now here,
It's a lot like younger rivers.
yeah, it might be, but you mean this one here?
No, that lasted also about 1,000 years, and it started after we got the warming.
Yeah, yeah,
And
That-
when we were recovering from late glacial maximum,
yeah,
then you get these three freshwater fluxes.
that's right.
And we went into the old Triassic cold period for 1,000 years, and then the whole
Yeah.
scene started.
Yeah, that's true. Yeah, it is a similar thing. Yeah, it might be. Yeah, I'm not sure how. Of course, it comes from a slightly different AMOC state from the glacial period, but yeah,
The pattern looks like it.
yeah. So it's not completely unrealistic, maybe. Now, what happens here on the right graph is, in addition to the melting Greenland in 3,000 years, we tried a lot of different possibilities for the Antarctic ice sheet to melt, the West Antarctic ice sheet, right? So all these colored ones are scenarios where West Antarctica melts always in 1,000 years. No, not always. Also, the duration is changed quite a bit between, I think, 500 and 1,500 years. And we start them at different points in time relative to the Greenland ice sheet, which is the black curve again. So that's the same as this one. And here below is the AMOC. The black one is again the one where you only melt Greenland, that collapses and then recovers. And the colored ones correspond to these Antarctic forcing scenarios. And you have very different cases that you see here. When West Antarctic ice sheet is melting early, the purple ones, then it looks like, so there's some variation in the AMOC, but it looks like it stays stable for a bit longer, but then it still collapses and recovers in the end. The yellow ones are actually the worst case. So this is when Antarctica melts at about the same time when Greenland is peak melting. So you have a lot of fresh water getting in there. The collapse is earlier, right? It stays longer in this situation with no AMOC, and then it recovers also later. The most interesting one, or the closest one to what I showed you before from the box models, is maybe the green ones, where you have an initial and early weakening of the AMOC, but actually it does not collapse, and it comes back. It only gets over a week. And because this is also a three-dimensional ocean model, we can sort of understand why that happens. And it does not work only via the density, but it works because there is a certain time delay. So the fresh water that you put in the Southern Ocean from Antarctica needs the time to it is transported into the north. And it needs a while to get there. And by that time, how to say that? So by that time, the Greenland ice sheet has started melting, but it does not affect a lot yet the AMOC. So because we look at the green curves. So this fresh water weakens the AMOC when it comes to the north, to the sinking regions, and that's why you see this early weakening. But at the same time, it moves the convection sites, obviously, to a place where it cannot be affected so easily by the Greenland meltwater anymore, because it moves a bit south. It gets weaker and it moves a bit south. So in that case, the Greenland melting does not have such an effect on the AMOC. And then when the fresh water from the south, at some point it stops, it gets weaker, then the AMOC actually can very slowly recover. At some point, it will also move back to its original northern deep convection sites, but at that time, the Greenland ice sheet has already stopped melting. So in that sense, it is not really affecting the AMOC. So it is a somewhat different mechanism than just with the density in these box models. But again, I mean, it is still an intermediate complexity model, and it's not so easy to see what that means for the real world. And in particular, I mean, there is this weakening there, which also lasts a few hundred years, right? Which on human timescales can still have quite an impact on a weaker AMOC on the climate. I think I'll skip this over and get to the end. So in the first part, I've tried to show you that it is very likely that indeed the climate sensitivity is not just a number, but it depends. It has uncertainty of measurements, but it also has uncertainty because the feedback processes vary over time. And if there are multiple equilibrium states possible on different timescales, that complicates a bit what we call this number, right? How we find it and so on. When we have long time series from paleoclimate maybe, or from climate models also, and there are these nonlinearities indeed, like tipping processes, that complicates a bit the estimate of that, but in general, it leads to the fact that we get these skewed distributions, or we get very long tails or something, extreme values in there. About the last part, I didn't talk so much, but the so these tipping cascades, they have, on one hand, they have the potential of affecting the global mean temperature, but on the other hand, they are really complicated and they're also stabilizing interactions. So it is very difficult to say what effect they really have on the global mean temperature. But they have a lot of regional impacts, which are, I think, to us, much more important than only looking at the global temperature index. Okay, I think I'll leave it by that.
Thank you so much. Now, questions? There were a lot of questions throughout the talk.
Yeah.
If there is any.
Yeah.
Yes.
Well, so in the recent years, I've seen many of these talks about, for example, about the AMOC, that once you include these like spatial dependency, that suddenly these tipping points are way less tipping points, but more some sort of cascade. So does that influence your story in any way, or?
So where this has been seen a lot is in ecosystems, right? Where you get these little steps in between spatial structure. And I think that where you see these little steps, this is in general in diffusive models. Now, it is possible that it happens also in other systems, but I have not really seen it very clearly so far. And my personal view on this is that fluid dynamics is quite a bit more complicated. So at least it's more than diffusion, right? So it's not, but there are also other mechanisms that could lead to these to other behavior. I mean, I think this idea of having two large-scale equilibria might be a bit put too simple, indeed.
And that's one of my.
Yeah.
Sorry, I'm not in the field, but I feel this climate should be a non-equilibrium steady state.
It is a non-equilibrium. Yes. Yes.
And do you know any model is like that?
Well, I mean, what you observe in if you really use the most sophisticated large climate models, these are non-equilibrium in a way, right? And you see a lot of effects on there, at least on the shorter timescales. On the longer, you don't see it because you cannot run them for so long. That's basically the limitations. So even if there are multiple equilibria, it is not so easy to find them in such models. And yeah, well, the other thing, yeah, with this tipping or not, I mean, it is very often more complicated than just having these two equilibria. But on the other hand, for the AMOC in particular, I mean, there have been an almost recent version of a climate model now done the whole full hysteresis. So you do for 1,500, no, I think about 2,000 years integrated with a very slowly increasing freshwater input. At some point, it really collapses. And when you go back to 2,000 years, you find quite a hysteresis. So it's not, yeah, these are still models, right? So it's not impossible, but I don't see it yet in some of these. Yeah.
You had so much information, so I might have confused you. I was confused about you put on the arrows, then you said stabilizing, destabilizing.
Yeah.
But yeah, I can at least think of two different ways in which systems can stabilize, destabilize. So it can be that they move them away from the tipping point, but it can also that they deepen the attractors.
Yeah.
There are many ways stabilizing can happen. So
yes.
What does that mean when you put stabilizing on the axis on a?
Yeah, that means, I mean, and these are, this is based on, well, very different studies. It's a bit more like expert elicitation than but some are model studies. But so what that means is that most of the times you see when you have a destabilizing effect. Well, let's take the example of the ice sheet and the AMOC, the Greenland ice sheet and the AMOC. I mean, you can think of different processes, but in general, you will have freshwater input in the North Atlantic in different regions, maybe. It will, in general, not lead to a strengthening of the AMOC. So that's what is meant by destabilizing. It will
Yeah.
typically lead to a weakening. It does not necessarily have to collapse it, right? It can also lead to variability or other things. While the stabilizing, if you go the way back, I mean, if you have changes in the AMOC, weakening or collapse or whatever, you will always get it colder on Greenland. So that should actually stabilize it. But yeah, already there is a bit of a problem because we don't know what it means for the precipitation. And even if you get it colder, it might still have no precipitation anymore. So you don't get the growth of the ice sheet anymore. So there is quite some uncertainty, but these arrows sort of indicate that in general, you would expect a destabilizing or stabilizing. So yeah.
Because the way I also think about these cascading transition models is that in generally the connectivity between all the subsystems is both a risk and a safety. So
yes.
Yeah, if it's well connected, then they keep them in place. So
yes.
But yeah, if it goes wrong, it all goes wrong. So
yeah, I think, I mean, but I think the fact that there are a few of these stabilizing processes in between there is sort of reassuring that it will probably not go wrong as a whole, right? I mean, you will never get all of these to tip, but the other interesting thing is the stabilizing interactions are very difficult to observe.
do you also have a model system where you, because this is so
yeah,
a model system where you can
where you try that, yeah. Well, we have tried some things, and there are also other studies having many of the same type of tipping systems and vary their interactions, and you find different types of cascades and so on. So you can find all kinds of things in there. The problem with that is that when you zoom in a bit, or when you go to the tipping elements in the climate system, at least, they are also different in their processes. That I have the feeling we need to focus on different 2 or maybe 3 of these systems, and every time there will be a different interaction in there, and we really need to understand the physics or the processes between there. So it is instructive to look at many of the same type in general, and you get all kinds of things that can happen. But if you want to decide what really happens, then you need to dive back into that. Yes.
If I look at this picture, almost all arrows sort of factor through the AMOC. Is
Yeah.
that because it's really sort of the keystone to the whole Earth climate system, or was this a study about the AMOC? Or
I
is
think
just the most studied?
No, I think it has also a physical reason, because the ocean transports a lot of information also from. I mean, it connects clearly the northern and the southern hemisphere.
More so at the Atlantic than in the Pacific.
Yes, because in the Pacific, well, because we don't have deep circulation in the Pacific so much. In the Pacific, we still have the wind-driven parts, but they are not so easily to change to a completely different mode. Yeah,
Okay.
yeah.
In the North Pacific, it's closed except for 70 kilometers of
Yeah.
start.
Yeah.
By Alaska and stuff.
Yeah.
So
that's why.
there's no connection between the Arctic Ocean and the Pacific.
Interesting, sure.
Yeah.
Barely connection.
Yeah. And also you have the Atlantic is much more salty currently. So it's easier to get this deep water formation in there. Yeah.
And related to that, so I could not help but notice that there are not many arrows to the right of AMOC. Is it because only there are some uncertain, I think, very limited evidence?
Yeah, this is limited evidence. I mean, doesn't mean that it doesn't exist.
So that's what I was thinking. Like, is it because there are less people in the East who are basically working on these topics and not known interactions, or is it because those are not really relevant?
Yeah, I think they could be very relevant, but there are few studies, and it's not only because there are not so many people working on it, but also because it is not so easy to study that. Okay. Because the focus has been very much on single tipping elements. I mean, there has been a lot of research on the AMOC, but what happens with the other systems that connect to that is not so much known, and you need a lot of model experiments to that and to do that. Yeah.
It's the Indian summer in reality. That's
Yeah, I saw that.
Yeah, that is currently actually quite some focus to study what happens as a consequence of AMOC to all the monsoon systems. Yeah.
And is it possible to track the constraints like all the heat flows or the energy conservation? Because if these are non-equilibrium systems, just have heat costs on top.
Yeah.
How about can you quantify the flows from data? Or it's not feasible?
Yeah, you can. I mean, we have satellite observations, right? So we can, for at least at the top of the atmosphere and at the surface, we can observe quite a bit. But these are never long time series. And in between, there are not always measurements of everything, of course. It becomes much more difficult when you want to know something about the deeper ocean, right? I mean, because there are not many measurements. And if there are very short time series, and they are point-wise and so on. So it is a problem of observations also, yes.
And also conceptual, I think, because just of measuring temperatures everywhere wouldn't give you the heat flow, because there's all these different ocean to ice to melting.
Yeah.
It's really very hard.
There has been, related to the AMOC, there has been an enormous discussion on having whether it's possible to have sort of sea surface temperature fingerprints of the AMOC, right? Because that would allow you to get further back in time, also from proxies, when you see a certain pattern in sea surface temperature. But that's very questionable that this exists, because the AMOC is not something that happens only at the surface, right? So it depends on what happens in the deep ocean also. And there have been other attempts to constrain that from the heat flux, which you can measure from, so atmosphere ocean heat flux, which you can measure from satellites and reanalysis. But it turns out that this is even more uncertain, actually. It doesn't constrain what happens to the AMOC, and it's still only a surface measurement, yeah.
Since about 2000, of course, you have the Aros floats, which
Yes.
enter the deep ocean
Yes.
until 2000 meters in
Yes.
quite a lot of detail.
Yes, that's true.
These are 4,000 floating buoys all over the oceans.
Yes.
Which are not active close to Antarctica and in the Arctic Ocean
because they get stuck in the sea ice. Yeah, that's true. Now, this is a good source of information indeed also. And there is also, since about 2000 something, 2004 or so, there is an array across at the line of 26 degrees north across the Atlantic that estimates the AMOC strength. So it has some measurement sites on the east and on the west part, and yeah, there you get sort of a global estimate. But that is still a very short time series, right? So that is. And in this time, there is no collapse happening, right? So
that's it. Because when I looked at these simulations, like even in scenarios of strong AMOC collapse, it takes 100 years for it to halve.
Yes,
or something.
yes. In the more sophisticated model, it takes about 80 to 100 years to collapse. Yes.
So actually, that's.
Yes, that's true.
We'll all be dead by then.
we are still the same thing.
Well, this is
Still no state.
Your grandchildren won't.
But they would be engineering the climate by that point. So.
Well, I think this is an interesting thing to note also to the public discussion. I mean, there's a lot of discussion about tipping points, right? But I mean, this is not something that happens in one day, right?
No, yeah.
And there is a transition period, which very often I think we also don't want to be in, right? Sure. Even the weakening of the AMOC for a few decades, we could have enormous impacts. It's not so important that there is a tipping, but there is a change.
I think we're already in a transition period. You see all kinds of changes in the climate.
Yes, for some parts, yes.
Changes in extreme precipitation, forest fires,
yes.
higher temperatures, and yeah.
Yeah, no, it's true.
There's a lot of talk about warning points for early warnings.
Yeah,
I think we're already getting these early warnings and you're just ignoring them.
Yes. That's true.
We apply the same type of modeling to social systems, psychological and social
Yeah.
systems. For instance, polarization, and there things can go much faster.
Faster. Yes, that's true. That's true. Yeah.
What is the element of society?
Yeah, probably US politics.
Yeah.
Okay, let us continue the discussion over lunch maybe, and thanks again Anna for coming. Thanks everyone for taking part in the discussion.
Yes, thank you.